Welcome to the video presentation of the final year project report based on Inertial Sensor-Based Hand Gesture Recognition System with SVM and Android interface. We will have an introduction with the problem statement, then we will discuss the overall workflow, the modules of the project and their basic components. We will also discuss about the graphical outputs that we obtain, and finally we will consider the future scope that can improve this project. The problem statement. We have considered individuals who are unable to communicate with speech. Their best alternative is sign language or meaningful hand gestures. But sign language is not understood by most common people. Hence, there is a misinterpretation, thereby leading to failed communication. The problem can be overcome by devising a gesture recognition system which will identify the gestures that are being made and convert them to speech. This speech will now be understood by most common people, and hence it will lead to successful communication. The overall workflow. At first, the gesture is being made. Then, the accelerometer and motion sensor data reading is recorded by the microcontroller. The microcontroller then transmits the data via a Bluetooth module. The transmitted data is received by the smartphone app. The app now sends data to server to test against the pre-trained SVM model. Data analysis and prediction identifies the correct gesture. We now have the meaning of the gesture. This identified gesture response is sent back to the app. Speech synthesizer converts response text to speech. The speech output is now made by the smartphone speaker. The modules. The entire system has three modules. The first one is the Data Acquisition System or DAS. It works by gathering the data from the inertial measurement units with the help of a microcontroller unit and streams them to the Communications Interface System app in near real time using a Bluetooth transceiver module in a specially formatted text. The next part is the Communications Interface System app or CISA. It stores the readings from the DAS in its buffer till the complete gesture is recorded. After the gesture is done recording, it sends the data over the internet using standard HTTP request to Gesture Recognizer module for either training or prediction based on the mode of the system being used by the user. It receives the predicted word from the GRM using standard HTTP response and converts the word to speech using text-to-speech engine. The final part is the Gesture Recognizer module or GRM. It accepts the data via a web server and employs special data pre-processing methods to extract features from the data. It either saves the processed data as a dataset and trains a model on that dataset, or it predicts this new data using a pre-trained model to give a word output which is sent back to the CISA for text-to-speech synthesis. Data Acquisition System. The main components of the DAS are as follows: the MPU6050 6-axis accelerometer and gyroscope sensor. The gesture data is being extracted from this sensor only. The TTP223 single touchpad detector IC. Every gesture is being made between two consecutive touches on the touchpad. The STM32 ARM microcontroller is the heart of the DAS. The HC05 Bluetooth module sends the data from the DAS to the CISA smartphone app. The AS1117 is a low-power positive voltage regulator used for power regulation on the DAS. The image on the left shows the data preprocessor and transmitter unit. It consists of the microcontroller unit and the Bluetooth module. It also has an adjustable wristband. The image on the right shows the interpreter gloves, which consists of the 5 IMUs, that is the inertial measurement units, and also the touch sensor module. Communications Interface System app. The CISA is the primary software interface between the user and the gesture recognition system. The app, when installed on an Android smartphone, appears with the name of Gesture. The app icon is shown in point number 1. This app is made with Thunkable, which is a simple drag-and-drop app builder interface. This app has two modes: the normal mode, which is the real-time testing mode. The user can use this mode readily to convert their pre-trained gestures to speech. The second mode is training mode. This mode provides an opportunity to train newly created gestures. Gesture Recognizer Module. The main components of the GRM are: the server. The data received by the mobile device is sent to a remote server to initiate the data processing. It is configured to serve two types of requests: for training new gestures and for predicting pre-trained gestures respectively. The server was coded in Node.js and the Express framework of JavaScript. The second part is the data extraction and pre-processing. Raw sensor readings for each gesture sample are appended into NumPy arrays and resampled along 50 uniformly spaced points through scaling and interpolation to create the feature vector for that particular sample. Training and model fit. A support vector machine-based machine learning model is trained with the available gesture dataset. The final part is gesture prediction. When the user makes a gesture for prediction, the data received by the server is stored in a particular text file and the prediction process is initiated. The dataset is fed to the SVM model to predict the class for this feature set. Actual and resampled signals. Now we see the analysis for one IMU sensor for one gesture. This graph shows the accelerometer axis X analysis. This is for axis Y, and this is for axis Z. Similarly, for gyroscope axis X, axis Y, and axis Z. Across the time axis, the shape of the resampled signal is almost similar to that of the original signal. These relative trends are considered as features for the SVM classifier, which is able to predict the outputs with high confidence. SVM classifier decision boundaries. The parameters chosen are C and kernel. The values of kernel are either radial basis function or polynomial or linear. These graphs show for C equal to 0.001. These are for C equal to 0.01. And these are for C equal to 0.1. Finally, we have C equal to 1. It can be seen that the best estimator is C equal to 1 for linear kernel, with a score which was obtained to be 0.81. Also, as C value increases, the hyperplane margin is reduced and lesser points are misclassified. Future scope. Convolutional neural networks will allow us to have large-sized class levels, and it also supports parallel architecture. Cloud deployment will ensure faster speed and increased scalable capacity. Users will have the independence of downloading sign language libraries, and the process will be entirely automatic. Bluetooth Low Energy will ensure low power and better connectivity. Calibration of IMUs with respect to each other is important because every time the circuit is switched on, a separate calibration would not be required. Thank you. Stay tuned for the video demonstration.
So this is our project, the gesture recognition system. So this is our hardware, this is our custom hardware, the entire system, like he is wearing. This is the interpreter gloves and this is the data pre-processing unit. It contains a Bluetooth which sends the data to the smartphone. Okay. So now we will be just training a gesture like he is doing. Like now start training. Do once more. doing the gesture for no, the word no. Now, we'll just show you how this app is getting the data. As you can see, the data for the no is being coming here and it is being sent to our server on the given server IP. As we can see, the data is coming to our server for server IP in our server. So we can see that the data is being streamed from the mobile to the server. Now let's just show you how the data is being stored in the files. See, 3 classes are being trained. The first class, yes, has already been taken. The no is here, and the food, that word is coming over here as of now. So these are the 3 classes that are coming.
Now we are going to create the data set from our collected sensor readings. So now I run the particular Python script to create the data set. As it can be seen, these data sets has been created for our collected readings. So the data sets have been created, as we can see from the terminal, and here in our directory we also see that a PKL file has been created for our corresponding data set. Now I'm going to train our machine learning model with our collected data set. As we can see, our model has been trained with a score of 1.0.
We have trained our model. Now it's time to predict some known gestures which are already pre-trained in the model. So now we have connected a speaker to our phone just to amplify the sound so that you can hear it. Here the phone app has got a text-to-speech engine which will be converting the recognized gesture into speech. Like Pritham will be doing the gesture for yes.
Yes.
See, the speaker says yes. Now Pritham will be doing the gesture for no.
No.
Now he will be doing the gesture for food.
Food.
So you can see that there is no universal gesture that is being recorded over here. Anyone, any user who doesn't even know the sign language can implement his own gesture, and that can be predicted quite accurately by the system.
Yes. Yes. No. No. Food. Food.
Very simple and cost-effective solution for gesture recognition system for people who are vocally impaired or are unable to communicate freely with other normal people. This is a very good